Carla Pugh is a surgeon and is currently the Susan Behrens Professor of Surgical Education, the Vice Chair of Education and Patient Safety, Department of Surgery, the Vice Chair for Innovation and Entrepreneurship, the Department of Surgery, Clinical Director of the Mock Portfolio Program and Health Clinical Simulation Program, and a Professor of Industrial and Systems Engineering, the Division of Trauma, Acute Care, Surgery, Burn, and Surgical Critical Care at the University of Wisconsin. She specializes in general surgery, is a member of the Department of Surgery's section of Trauma and Acute Care Surgery. As I mentioned earlier, she's going to be joining Stanford this week, and she's going to talk to us about sensors for physician excellence.
So 3 years ago, I gave a TED Talk on sensor technology and its potential to dramatically change the way that we measure and evaluate hands-on skills in the medical field. During that talk, I introduced the concept of a haptic score. And this is a measurement that can be obtained when using sensors to evaluate exactly what it is that clinicians are doing with their hands during medical procedures. 3 years later, and several experiments later, I am completely convinced that sensor technology can transform clinical medicine. I'm trying to advance my slide, okay, and actually improve the quality of care that we provide. And I believe this for two reasons. One, sensor technology has the ability to help us provide feedback to surgical trainees that has never been available before in healthcare. Sensors can also help us to quantify expertise, and that is something that's desperately needed if we're going to be able to set standards for procedural medicine. What you see on this screen is actually the traditional training paradigm in the medical field. This patient has bilateral inguinal hernias, and this is a perfect scenario from a teaching perspective because I then get to demonstrate how I do a hernia repair for this trainee, and then after I do the hernia repair, he can do the hernia on the other side while I give him feedback. Now, all of you should know that I pride myself in being an excellent teacher. In fact, the feedback that I provide all my trainees is actually pristine. It's perfect. But I also know that there are specific metrics that actually are important for learning procedural skills that can't be observed or tracked by the human eye. And force is one of those. So what I will do in the next 20 minutes is explain to you the research that I have done as a surgeon scientist using sensors to extract force profiles for various medical and surgical procedures. Over the past 20 years, our research laboratory has fabricated over 30 different clinical and medical scenarios that physicians are then performing procedures, and we are actually able to collect data. Most of this time we have spent actually analyzing the data to understand what it means with respect to performance. What again, are the signal to noise profiles of the data that we're capturing. What's the best sensor? I will go through my story and tell about 5 sensors that we've used, but we've used and broken over 20 different sensors during that time. Over the years, we've collected data from over 17,000 physicians. The first sensor that I learned about was in force sensing resistor, and that was in 1997 when I was actually a grad student here at Stanford and taking a class on human-computer interactions. It was a course that was taught by Terry Winograd and Bill Verplank, and one of my classmates and I learned how to instrument the sensors and put them on the organs of a training mannequin that existed for our medical students. And what I will show you is actually some of the data. It's actually for 2 medical students that performed a bimanual examination of the uterus. And what you'll see are different colors, which represent the sensors that are placed in specific areas of the anatomy within the uterus. So the purple sensor is on the fundus of the uterus, and the other colors are on the cervix. The blue is in the anterior, the turquoise and yellow are right and left posterior, and the pink one is on the os. So you'll see this line graph of all the different sensors that were activated, and this is actually a really good examination. What this person is doing, and you could see the amount of force applied over time, obviously this is the sampling rate really. This person held constant pressure on the left posterior part of the cervix, and then did several high amplitude palpations of the fundus of the uterus. And those forces were between 6 and approximately 9 newtons force when they were doing this examination. This is a really good exam. Now the next one I will show you is one that was not so good. And unfortunately, I had to distort it to fit it on the screen, but you can see the difference. This person touched various parts of the cervix in numerous different ways, and took twice as long to do the exam, but was barely able to find the fundus of the uterus at the end of the procedure. What's really striking about this is that this is what the data shows, but if you were to observe, and I was observing these two students and their posture while they were doing the exam on the sensor-enabled mannequin, and I knew that one student took longer, but I can tell you if I were to give them a grade based on human observation, I would have given them the same grade. Their posture was appropriate, their language was appropriate, but obviously what was happening was night and day. And that was when I knew there was something here in terms of these sensors. I ended up doing my dissertation on this, and then obviously have continued this research. After collecting data from over hundreds of students, we then took the same training mannequins, or sensor-enabled mannequins from different companies, and collected data from experienced physicians that lined up by the hundreds at a medical conference. So this is actually, and I'll show some of the other data we've collected, this is how we've been able to build a database of physicians by taking all of our technologies to the appropriate medical conference, and every single time the physicians line up by the hundreds. Now, many of them who are overconfident are wanting to come so that we can tell them that they're actually the best and that the technology proves it. The rest of them, they all want to know, how did I do? How did I do? And we give them that feedback with the sensor outputs. And this is some of the data that we've collected early on in my career. Big difference between the way students perform the exam, which you expect, as well as experienced physicians. When you compare the two, there's a difference in time, the amount of pressure or force that's applied, and the frequency at which they touch the various areas of the anatomy. So I was awarded a patent for the use of sensor technology to capture hands-on performance during medical procedures, and I gave a license agreement to a company, and they manufactured this simulator in 2001. They sold over 200 units for $20,000 a piece and distributed this worldwide. What was good for me in this was that it helped me to collaborate with a wide variety of colleagues that were able to look at the data in different settings with different groups, and it really actually confirmed the reliability and the validity of the force profiles that we were capturing. And we were able to show that there is actually a specific force profile for many different clinical procedures that matches someone's ability to generate a correct diagnosis. And if your force profile looks different for that specific procedure, it's likely that you're going to miss the diagnosis, you're going to get something wrong. And that was really rewarding and also motivating to continue with this work. So when I think about the FSR, you know, a lot of folks have talked about the variety of sensors. We still use the FSR, but we do know some of the limitations. As Zin and Bao mentioned, that hysteresis is an issue. What we learned, especially with the bimanual exam of the uterus, it's mostly 30 seconds with the experts. It's 1 minute for those who are not experienced. After about 3 hours of continuous use, we'd switch out the sensor-enabled organs because the quality of the sensor output would go down. The other issue that we had was that we know that in the medical field, people use shear forces when they're doing examinations of organs. And we could see some of the movements in the waveform of the data, but we weren't able to extract it. And we know some of the FSR was missing some of this. So hysteresis, shear forces, that was a problem, and that put us on the hunt for a better sensor. After I left Stanford and went to my first job at Northwestern University, I was lucky to collaborate with Chang Liu, who is an engineer who was just moving from Urbana-Champaign to Northwestern, and he thought, the hair cell sensor could definitely detect shear forces. And so he proposed using this sensor and built several of these models, several of these sensors for our models. And it was perfect in terms of doing shear forces and giving us some data. Unfortunately, we broke all of them. The durability was just not there in terms of its ability to withstand the 10 or greater newtons of force that many of the students and experienced clinicians were applying. But at least it gave us hope that we could extract shear forces and characterize it more readily than we could with the FSR. So he then tried something that's a little more durable, a 3D sensor. Basically, it's a sensor made with several layers of silicon and basically oriented in in the XYZ space. The issue with the sensor is that it was contained within a mold of PDMS, and while it was great at detecting shear forces and it had fantastic durability, it had limited use because the clinicians could actually feel it. So we were able to use it as a tumor, but not as something that could detect forces without having the appearance of an abnormality. So what we ended up doing, we did some pilot studies where we had this sensor as the actual mass in a breast exam or other tissues, and then we used the FSRs for the other parts of the tissue to understand exactly what it was that someone was doing while they're performing a medical procedure. Again, still looking for the perfect sensor. In 2012, we actually resorted to a commercial sensor, and this is one of the tech scan sensors that has over 1,400 sensing units, and it was perfect for the clinical breast exam mostly. And I'll show one of the things that we were able to do was quantify physician expertise. It did not have the problems, the hysteresis problem that the single FSRs did, which was fantastic. And we were able to map exactly the difference between an accurate exam and an inaccurate exam for hundreds of clinicians. We ended up collecting data without any problem from 550 physicians using 4 different clinical scenarios, 4 different patients. And they were all presented as unknown. And we collected those data at 3 different meetings over 2 years, meetings for the American Academy of Family Practitioners, the American College of Obstetrics and Gynecology, and the American Society for Breast Surgeons. And what we noticed is that, again, for those who were able to find a lesion, there was a significant correlation between the amount of force applied and accuracy. And it turns out if you applied less than 10 newtons of force during a clinical breast exam, you're 70% more likely to miss a lesion. And 15% of experienced clinicians, regardless of specialty, regardless of number of years in practice, regardless of number of breast exams that they do on a weekly basis, 15% of them don't apply enough pressure to even find a lesion. What you see here, we were able to sync video with the sensor matrix that we had, the force map, and you can see this is an example of someone who got it right and someone who got it wrong. The person on the top missed the lesion. They touched it several times, you could see it light up, but they ended up not touching it with enough force to recognize that there was an abnormality, and they wrote on the clinical documentation form for this breast model that it was normal. The next slide that I will show you relates to actually the kinematics, what it is that people do with their fingertips. And we were able to categorize 90% of those 550 physicians into 3 categories. 1 that had been described in the literature before, but 2 have not. I had seen it over the years, but it just wasn't described in a textbook. And what we realized is that a lot of people use techniques with their fingertips that had just been handed down by tradition. Who did you learn the breast exam from? You mimic that. And we were seeing these repeat use of certain maneuvers. Looks like the video's a little glitchy, but there are people who are rubbers. They do this rubbing technique. There's some that do this vertical movement, and then there's the piano fingers people. And when we looked at the data and put it in a linear regression, it turns out that those who do the piano fingers, independent of force and independent of all the other variables, those who use the piano fingers techniques are 4 times less likely to find a lesion compared to those who use the rubbing technique. And this is something that's never before been described in medicine. So this was a lot of fun for us because we had a great sensor that had, unlimited durability and the ability to look at shear forces, directional forces, and mapping of all of these. We then wanted to take it a step further. So what we did was take all of the physicians that got the right answer on all 4 models. And then we wanted to know who were the physicians who did it in half the time? What is it that they do? Do they do something different than their colleagues? And we're really after the Olympians. That's what we wanted to know. Who is the best of the best, and what does it look like? Really, really curious. How can you not ask the question? So what we found is that all of the Olympians apply greater than 10 newtons force on average during a breast exam. We also found that a significant number of them used the rubbing movement technique compared to the other practitioners. And again, the rubbing technique is what you're doing with your fingertips at sort of the micro level. Then they cover the breast tissue using this rubbing technique. So that's the search pattern. This is the HAPIC score for an excellent breast exam, or for a gold medalist, if you will. We then compared the gold medalists to those who didn't make the Olympics, those who only got 2 lesions and they did it very slowly. Big difference in the amount of force, and it turns out force is one of the most predictive factors of whether you're going to be accurate when you're performing a clinical breast exam. It turns out rubbing is not the only technique that the Olympians use. They do that vertical movement, and a few, not many, a few of them use the piano fingers technique. But here's the difference. It's the amount of force when you're using that search technique that really makes the difference. And again, force is one of those things that can't be tracked by the human eye. And currently, the gold standard for credentialing performance for all procedures in medical field is human observation. So what about other procedures? I've talked about the intimate exams and probably have made a few of you kind of squeamish and nervous. All right, we've got other profiles that we are now mapping. And again, we've done this for over 30 different medical procedures. This project, we worked with the Department of Defense for this new tourniquet that they applied for junctional hemorrhage. And again, there is a classic signature, a force profile for when the tourniquet is applied appropriately. And when it's not applied appropriately, the waveform looks differently. You can tell the difference. Same thing for an intubation, something that's done commonly every day by anesthesiologists, by emergency medics, those persons who come to help someone down in the field. Novice intubation, not only does it take 3 times as long, but you can see the difference between a novice and an experienced intubation. Thyroid exam, we're just getting started, but this is the force profile of an expert. And we were really interested in a thyroid exam because it's just a little different. And, everyone uses 2 hands well, most people do. And part A was just when they're placing and identifying landmarks in the anatomy, and they use some different palpation pressures there. And then they ask the patient to swallow, and they hold a little more pressure on one side as they're examining the left side of the thyroid gland, and then they ask them to swallow again, and then they hold a little more pressure on the other side. And so there's a specific profile that happens again, and so we're now collecting data, large amounts of data from the experts and novices so that we can see the difference. This one's even a little different. This one is when our clubfoot babies undergo serial casting in order to correct the angulation of their foot so that they can actually walk. And it turns out that when you are placing a cast on a clubfoot baby to help straighten their ankle joint, you're not supposed to touch the heel. And so this is the profile of an expert. And obviously, if we are starting to put sensors on clubfoot babies or even on the casting stockinette, which is commonly used before you put the hardened material on, we'll be able to sense this and actually track what it is that physicians are doing. So when I think about the sensor matrix, that really changed things for us in terms of our confidence in our ability to find a sensor that has the durability and can help us collect data and analyze shear forces. But again, we're still on the hunt for the perfect sensor because this one is not flexible. It can't be placed on all body parts. And it's limited in terms of the location that it can be placed, even within the breast exam. Some people who do the light padding, we would like to have a superficial sensor plus the sensor matrix on the bottom so that we can collect more data. Again, when I think about our experiences using sensor technology over the years, we have always found some pros and cons of each sensor. We explored some of the flexible fabric sensor. We're excited with what we've heard today with a lot of the sensors that you all are developing here in the audience. We explored a number of the flexible fabric sensors, and some of them had durability issues. Some of them were too thick and, again, not deformable enough to encase on a body part, whether we're putting it on a mannequin or, as we are now doing, on human beings. We did find one sensor that was flexible enough to be cut into 5 sensing units and then put in the form of a breast so that we can add as a layer to our breast simulator, but we also then built an early pilot for a standardized patient. And these are women and men that allow medical students currently at all medical schools across the country to do physical exams on them, and then they give them verbal feedback. Well, if we could add sensors to the mix, then the students can get a lot more feedback than they're currently getting. But this is really the end game, getting sensors on patients as well as on mannequins, and I'll explain that. I think when I give these talks, I'm usually get really, really good feedback, and folks are excited about the potential for using this technology to improve the quality of care. But everyone always asks, do doctors really want to be tested? I mean, why would a doctor want to be tested? And I have to say, in our experience, the answer is yes. They line up by the hundreds. But the key thing here is that we are testing them in a safe place. It's their data. I'm not the regulatory board. I'm not a hospital. I'm not a credentialing agency that's going to say, if you don't perform, if you don't get this metric, then you can't practice medicine. Of course, no, who wants that kind of feedback? So the doctors line up here, and it's a safe place. Again, they line up by the hundreds, the thousands, and they want the feedback. So I think there's a huge opportunity here to actually really improve the quality of care. And like I said, the opportunity is just, it's unquestionable that there's an opportunity. Sensors can transform procedural medicine. Wider variety of technologies that are being developed every day, and I'm really excited about what I've heard this morning and looking to see what groups I can collaborate with to get sensors that work with the mannequins and on patients for collecting data that is durable and valid and reliable with respect to hands-on skills in the medical field. I think when you look at sensors on mannequins, it seems kind of a crude thing, but the one key point with it is that I can get 100 different physicians from different backgrounds to do the same exam, the same clinical scenario. We can fabricate abnormalities. I can simulate over 100 different patients with the breast models. And that then enables us to build a performance database and get a haptic score that sets a standard. I mean, if you think about the Olympics, you have to know what the actual scoring is. You can't compare a skier on one mountain with another and then say, you know, who did the best, because they're facing two different things. So at least if we have some understanding of what the standard metrics are, once we then put the sensors on patients and start to use this in clinical medicine, we'll at least have some point of departure of what the real metrics are. Otherwise, you're comparing apples to oranges if you go directly to patients without having that understanding. Ladies and gentlemen, thank you, and may all of your physicians be Olympians. Any questions? Hi, thank you.
So one of the things that's inherent in this is picking the gold standard to be able to decide whether or not what you're measuring does or does not measure what you want it to. So in the case of a breast lesion, for instance, the gold standard, is it there or is it not there? In some of these other things that you'd like to measure, for instance, surgical techniques, you would really like to correlate some of what you're trying to measure with hard clinical outcomes to be able to decide whether or not something is or is not better than something else in terms of methodologies, performance, et cetera. How do you propose to come up with these gold standards for the great majority of what everybody really wants to know in terms of is a physician, whether it's a surgeon or somebody else, good or not good or better than somebody else or not better?
Yes, that's a great question. And the fun in it is that the gold standard exists in the practicing clinicians. If you talk to a bunch of surgeons and you ask them how they do something, the reason verbally you think that they can't agree is because their metrics are verbal. It's different. If you measure what they're actually doing, again, you will find an Olympian signature. The surgeons who are excellent, there are commonalities in what it is that they do. The metrics aren't obvious to them because they've never been measured, but every single time we instrument a mannequin or a surgeon, and it's a short talk. I wasn't able to talk about us putting sensors on surgeons, and we're beginning that work. But every time you measure them, there are commonalities in how the experts do it. One person may start on the left and proceed to the right. The other one starts on the right and proceeds to the left. But what they do in between, there's some commonalities that are very different than the outliers who have worse outcomes, who take longer, and who are not Olympians, for lack of a better way of explaining it. So I love the question, and that was actually a number of the warnings that I got even before doing a simple procedure such as the breast exam. Everyone said, oh my goodness, you're crazy. There's unlimited degrees of freedom. No physician does it the same. You're never gonna find anything. That's what I was told 20 years ago. And so I think that with the right sensors, with the right data, we can make the standards explicit. And I'm excited. I think there's a lot that can be done. Thank you.